Any questions? Yes. 6-1. So, oh, I can't move it on there. It's on here. 61. Oh, that one looks like fun. Wow. Oh. I was working on this with somebody else yesterday, and I was like, I knew this should be able to combine, but I was having trouble seeing it yesterday. Hey, look at that. So, if you take a look, there are 2 different ways you could do this problem, and it just kind of depends. Apparently, if I had done it this way, it would have been a little easier to see. What I was thinking when people were asking me, I made these several years ago. I'm going to move it down just so I can point. You have 2 different terms here. And this first term doesn't have a natural log, but this term does have a natural log. So you could, and this would totally work. It'd be totally fine. But apparently, trust me, it gets a little messier actually in this case. But you could treat these as 2 separate problems and then add them together. So with this one, this term, without the natural log, you could do that whole take the natural log of both sides, expand, and then find the derivative. And then over here, you're already set to expand. So you could do it that way. Apparently, I didn't. So, and actually, I take it back. This one doesn't expand now that I look at it. It's got a plus sign. This won't expand at all. So instead, just look at it this way, where the first term I did quotient rule. So remember, bottom times derivative of the top plus top. Or minus top, that's why it's plus sign, over derivative of the bottom, which would just be 1, over the bottom squared. And then over here, then remember the derivative of a log is 1 over the argument times the derivative of the argument. So this is just quotient rule and then the natural log rule together. And then it's just a matter of playing around with it. So any questions about that? And then I was looking at it yesterday, and when I did the logarithmic differentiation on this term, but not on that, like I did see the x squared plus 1s coming up, and it just seemed like there should be something you could do. It was not nearly as obvious as it is in this case, what you can do to simplify the problem, because I'll move it up now. Because you can see it does simplify down pretty nicely. As far as a free response question, honestly, just like I was saying last time, it's okay if you don't combine to a single fraction and all that. I mean, ideally, if it does simplify down to something like this, you do. But if it doesn't, you don't have to. But the question is, something as messy as this, how do you know it's actually going to simplify down to something like that unless you actually go through the work of simplifying down to something like that? And the answer is you don't. It is, I mean, when you do the problem up there, there's x squared plus 1s showing up everywhere. So it does seem like something's going to happen, but it's not obvious. So for my test for a free response question, just like I was telling you guys last time, if you don't want to combine it to a single fraction, you don't have to. I will say in directions if I want you to, because I might want you to practice it. I'm only going to have you do it, though, if it does simplify easily and nicely, because I still want you to practice those skills. But if it doesn't say it in the directions, you don't have to. Now, if it's a multiple choice question, that's different. But if it's a multiple choice question, I've never seen it. I wouldn't do this to you, and I've never really seen a standardized test made by somebody else where, like, some of the problems or some of the answer choices are simplified and some of them aren't. I shouldn't say it that way. Some of the answer choices are combined into one fraction, but some of them aren't. Unless, like, nothing like this. Anyway, so look at the answer choices. If the answer choices are combined, then you're going to have to combine it. So, that was kind of a long drawn out, because I have a feeling that's probably where the questions were, like, oh my God, do I have to combine it or not? Any questions? Either how, I mean, I can still walk through how I combined it if you want. Any questions either on how I combined it or all that other stuff I was just saying? All right. Any other questions? Well then, You know the routine. Let me have your homework. And we're going to take a reality check. Yeah. So I shall pause this video. For you people watching the video, goodbye. Number 1. And then we're going to jump to number 4. But any questions about number 1? We're number 1. We're number 1. Tough crowd this morning. It's Friday, you guys! Okay. Any questions about number 1? Don't forget your properties of logs. Ready for number 4? Remember, we're jumping down to 4. Here is 4. Well, hello there. Any questions about number 4? There's a lot going on number 4. But you can see you don't have to combine it all. Yay. Anybody want more time looking at number 4? Here's number 2. And, oh, I can get it. There's 2 and 3. So in order going down, the answer should have been B, C, D, C. Ah, too bad it wasn't A, C, D, C. Yeah! Yeah! Need to play a little Thunderstruck. Any questions over the reality check? Hopefully you guys are still finding it useful to practice what you learned. But a little lower stakes, feel a little better. Ready to do some notes? Ready to talk about integration with natural logs? We're going to do it anyway, damn it. I mean, darn it. I didn't say that. Shh. I gotta watch out now. Everything I say is being recorded. All right. Let's see here. Period 1. Let's get a new notebook going. Oh, hey! You know what? Today's my cat's birthday. I know you care. He's 11 years old now. Let's all say happy birthday to Louie. Happy birthday, Louie! Okay, there you go. This is section 5.2. Ooh, not 5 times 2. 5.2. Natural logs. Integration. All right. Now we're actually not going to take the integral of just natural log. That actually requires something else that we don't know how to do yet called integration by parts. We may or may not do that this year. It's actually a BC topic, not an AB topic. Although it's one of those things I usually cover in AB. We'll see how time goes. Maybe it'll be something I do after the AP exam. That one's a basic enough one. And important enough. So anyway, natural logs integration. Recall from last class that the derivative of the natural log is 1 over x. We did that last time. Well, then we can kind of reverse this whole thing and turn it into an integral problem. This means that the integral of 1 over x dx, the antiderivative, is the natural log of x. But then we know we just have to add plus c. And there we go. That's pretty much it. Except we put one tiny little twist on this. And it's not that big a deal. But remember that the argument for a natural log has to be positive. So we force it to be positive by just putting absolute values. And there we go. There it is. There is our notes for today. We're done. Okay, let me stop the recording. Just kidding. But that pretty much is it. Everything we do is going to be based on that little tiny equation there. Now, if I expand this idea, remember we also did the derivative of the natural log of some function of x. So remember that was 1 over the argument times the derivative of the argument. We wrote it u prime over u. So we also have this then that we can turn into an integral. The integral of u prime over u dx is the natural log of u plus c. But then just like we did for the last formula, we can only take the natural log of something that's positive, so we force the argument to be positive by putting absolute values on it. And there is our other very important formula. And honestly, this is the one we're going to be using more often, because life is just not usually as simple as 1 over x. So here's the general thing. If you have a fraction in your integrand, one of the things you should be asking yourself when you're trying to figure out how to find the antiderivative of it is, do you have the derivative of the bottom in the top? And you're going to hear me say that a lot. The derivative of the bottom is in the top. It's a natural log problem. Derivative of the bottom is in the top. Derivative of the bottom is in the top. Natural log. It's a natural log if the derivative of the bottom is in the top. I read somewhere that you need to hear something at least 20 times before you remember it. What was that for? The derivative of the bottom is in the top. It's a natural log. I'm just kidding. Say it with me. The derivative of the bottom is in the top. It's a natural log. You didn't say it with me. The derivative of the bottom is in the top. It's a natural log. Say it as fast as you can. The derivative of the bottom is in the top. It's a natural log. They are not saying anything for people listening on here. You're saying it in your head, though, right? Right? Oh, okay. All right. I'll take it. All right, let's just do a whole crap ton of examples. And yes, I said crap ton. We may not do all of them, but some of them will be very quick. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 examples. But don't worry. Like I said, some of them are very quick. Let's just do it. Andrew, what's your favorite color? You don't have one? Oh, David, what's yours? Blue? Okay. We'll go blue. Burnt yellow. Puke mustard. Ugh. Anyway, like pea green. Looks like puke. Sorry if that's your favorite color. Anyway. All right, first example, very simple, but let's just start off. We're going to build slowly. Ponder this one, if you will. James, what's your favorite color? Green? Okay. We're going to put the answers in green. Raise your hand if you think you have the answer to this one. If you're thinking it can't be that simple, actually it can. This is a simple one to start with. Suvrith? Excellent. That's exactly it. You definitely do not have to write this out, but remember that 3 that's in front, you can just, anytime you're multiplying by a constant, you can just factor it out of the integral. And then it's exactly one of the formulas I gave you up above. So you can just go to the final answer on this one. But just for our notes, I wanted to put that in there. There it is. It really is that simple. Yay! Now, I will say, normally, I'm not a big fan of being sloppy in how we show our work or say things, but, oh, yes. Yeah, you could. That's a good point. If you didn't hear what he was saying this. Can you make it an exponent? And yes, you can. And that actually brings up a good point, because if I cube x, does that make it always positive? All right, okay, so I still need the absolute values. But if this was a squared, then x squared is always positive. So if we rewrite it like this as an exponent, you can actually drop off the absolute values at that point because it's already always positive. So yeah. You'll hear, and I am this way too, and I apologize, especially, I try not to be, especially in the beginning when we're first learning this, but you'll hear a lot of people just read the answer to this as the natural log of x and not say the absolute value. It's kind of implied because it's kind of understood that when you take the integral, the absolute value is there. So we get a little lazy, I have to admit. But it really is laziness. It is not correct to say it. So I'm glad that Suvreth was good. He said it. Yeah. All right, there we go. One example done. 8 more to go. Any questions on that? Aight. Then the next one. The integral of 2x plus 1 over x squared plus x plus 3 dx. Dun, 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 dun. Ponder this one, if you will. Take a moment, and then we'll look at it together. Now I've got Yellow Submarine going through my head. Our brains are weird, aren't they? Yellow Submarine. I think it's because someone said yellow. Who was it who said yellow? Was that you, Suvreth? He's like, it wasn't me. It wasn't me. All right, so with this one, you either see it or you don't now. So I'm going to just see. Anybody notice anything in this problem? Charlie? Wait, do we have the derivative of the bottom and the top? Oh, that's what now? Am I up to 8, 9 times now? The derivative of the bottom is in the top. Look at this. The derivative of the bottom is 2x plus 1, which is in the top. Sweet. What does that mean, though? Oh, yeah, it's a natural log problem. Ugh. And it'll be the natural log of the bottom. Don't forget those absolute values. Ta-da! Don't make it more complicated than... I can't speak. Words are hard. Don't make it more complicated than it needs to be. I'm just going to put a little... The derivative of the bottom is in the top. Hooray! Yes?
Do you need the absolute values for that function because it's always positive?
So here's the thing. How do you know it's always positive?
It doesn't have any roots.
How do you know it doesn't have any roots? Okay. So, yes. This thing right here, it's a quadratic, the argument. And so if you were to check, and can you remind us how you check to see if it has any roots?
I use the quadratic formula.
Yeah, specifically which part of the quadratic formula?
The square root part.
Yeah. So remember the quadratic formula, you have that square root, the square root of b squared minus 4ac. If you work out b squared minus 4ac and you get a negative, then you're going to be trying to take the square root of a negative, which has no real solution, which means this thing has no roots, which means this parabola never crosses the x-axis. And because it's a parabola that smiles, it has to always be above, so it always has to be positive. That is a lot to kind of put through your brain, isn't it? So the question was, do we need absolute values on this because it's always positive? And the answer is no. Now, in general, it's not really simplified if you have the absolute values and you don't need them. Although something like this, I mean, it's not that much work. but you'll often see that this just gets left with the F. Basically, I'm going to say, unless it's super obvious, it's okay if you leave the absolute values on when you don't need them. And what I mean by super obvious, if your answer was the natural log of x squared, that better be super obvious that that's always positive. So any even power, of course, will always be positive. If you have the natural log of a square root, square roots are always positive. So you won't need the absolute values there either. But something like this one, he'll be okay. But you're right, we don't need it. Very good. Any other questions? See? Easy peasy lemon squeezy. Let's try another one. Isn't this fun? 2 down, 7 more to go. Woohoo! Next example. The integral of 2 over 4x minus 1 dx. Just take a moment to think about it, and then we'll look at it together. Do we have the derivative of the bottom and the top? Yeah, almost, but not quite. Almost isn't good enough. What do? We just throw our hands up and say we can't do it? Well, I'm glad nobody said yes to that. But nobody said no! We are mightier than that. We don't need to. Anybody got an idea what we can do on this one? Charlie? Do we have the derivative of the bottom and the top now? Oh. So we still have to do some. Suvrith?
You can factor out a 1/4.
We could. The only reason I don't want to do that is if I factored out a 1/4, it's going to turn that into a 1/4, and then we'll have a fraction and a fraction. But you're right. We could. Or, Mason?
From the original equation, I factored out 1/2 to get 4 over 4x minus 1.
But you still have a fraction then, don't you? A fraction in the bottom? If you factored out a 1/2, you'd have to factor it out from this 1 also. Ah! Trey!
I multiplied the integrand by 2 and then outside the
Yeah. Look what we can do. And we could do this with the green one also. We could do something similar if you got this far. I didn't see it. But right from the very beginning, the derivative of the bottom is 4. Oh, we have a 2. But we're only off by a factor of a constant. All we have to do is multiply by something, and we get the derivative of the bottom and the top. So you know what? Do it! Just put a 2 in there. Make it 2 times 2. Change the problem. Oh, but wait, we can't actually just do that. We'd have to keep it equivalent. So if I multiply by 2, I also have to divide by 2. And I can do that on the outside. Because remember when we were going... Oh no, it was the very first problem here. Remember when you are multiplying in the integrand, you can factor that out of the integrand. And so that's basically what I'm doing without showing that step. I'm just putting the 1/2 on the outside. But now it's balanced, it's equivalent. And we could do the same kind of thing over on the green one. So like let's say you got to the green one and you're like, oh shoot, I could do that. You can. Now you'd have to multiply by 4 to get the derivative of the bottom and the top. But then you'd have to divide by 4. You still wind up with the 1/2 on the outside. So it works either way. But now we got it. The derivative of the bottom is in the top. So does it make sense why we can do that? So if you're just off by a factor of a constant, put it in. And then we have the answer. 1/2 natural log of the bottom. And you can write your answer like this, or we're multiplying by a half. That's the same thing as if you have a square root. And just like we were talking about before, when you take the square root, that's obvious that it's always positive. Don't put the absolute values there. Yeah. So you're talking about just doing power rule?
No, like when you got to 2 times the integral of 1 over 4x minus 1 y, you just do like, I'll leave it at that, and just do the next 2 times the natural log of 4x minus 1.
Oh, okay. So let's take a look. It might help if we check it using derivatives. So the question, looking at the green one we have, I'm just going to put it off to the side here. If we have this, why isn't it just this? Oops. Yep. Move it over a little so it's not so squished. That's what you're asking, right?
Yeah.
So, yeah, let's take a look. I mean, why can't we just take the natural? I mean, it's just like 1 over x, right? Except it's 1 over 4x minus 1. So why can't it just be that? And if you go to take the derivative, because remember we should be able to take the derivative of this and get the integrand. So let's check. Check derivative of 2 natural log. By the way, when you're doing this, you can ignore the absolute value on that. So I got the 2, and then remember 1 over the derivative times the derivative of the bottom. 1 over the argument times the derivative of there. Oh my gosh, I'm getting my little phrases mixed up. When you take the derivative of a natural log, 1 over the argument times the derivative of the argument. But is this going to be equivalent to that? What do you think? I'm not hearing anything. I see your head shaking. Anybody have anything? Anything they notice? Any comments? Anything like that? I'm gonna make you guys think about this one. Trey.
In the fraction of blue, the denominator is 2, but in the fraction, I mean, sorry,
Say it again. Sorry.
in the blue fraction, the numerator is 2, and in the fraction, the numerator is 2.
It's the very last one. What's the numerator in the pink one? 8. Wait. Oh, right here. Yeah, exactly. It's not quite the same. It's close, but not quite the same. This is equal to 8 over 4x minus 1. But we only wanted 2 times 4x minus 1. So that 4 really is throwing us off. We need to put that 4 in there. Yes?
Then what is the formula not work?
Well, the formula says the derivative of the bottom should be in the top. So that's the thing. Even though this is just a plain old x, because like here, yeah, that's 1 over x to the first power. I don't know if this is what's throwing things off. And then it's just the argument. We don't have to worry about anything. But that's just because the derivative of the bottom is 1. So the derivative of the bottom is in the top. But on this one, the derivative of the bottom is 4. And that's not in the top. The derivative of the bottom has to be in the top to just say the natural log of the bottom. Doesn't- Maybe as we go on.
No,
I'll
I
check.
know,
Okay.
I thought like it was just the 1 over the bottom. I get it.
Yeah, you always have to have the derivative of the bottom and the top. All right, any other questions? Oh, yes.
For the second answer, would you still need absolute value bars inside?
You mean this guy right here?
Yes.
Nope, because remember the absolute value is forcing the answer to be positive, but the square root already does that, so you're good.
I was wondering though, because the second answer has a different domain to the first answer.
Well, okay, I see what you're saying. This is then, I mean, I know it's kind of weird. We typically don't. I see what you're saying. I never really thought about it, but you typically won't see it because it's kind of implied now with the square root that the answer has to be positive. But then that begs the question, why do we put the absolute value on the natural log? Because that kind of is what we do. I don't know. Yeah. You typically won't see it, though. You won't see it put here with the absolute value because it's already implied with the square root. Because we don't take the square root of negatives. I never thought about that, why we do on one and not the other. Well. Any other questions? All right. Let's try this one. You guys take a look at this one. Example. The integral of 3x plus 2x cubed over 3x squared plus x to the fourth dx. Oh, shoot. I meant to freeze it. What you gonna write? I want you guys to think about this. Anybody think they got the answer? Charlie? Perfect. Excellent. Yeah. Oh, yes.
For the second one, I took out an x squared, so it had a natural log of absolute value of x times the square root of 3x squared.
You could do that. Yeah. Yeah. So again, you see a fraction, ask yourself, think about what's the derivative of the bottom. And if you need to write it out when it gets to be a little more complicated like this, feel free. But the derivative of the bottom should look like that. Compare that to our numerator. Not quite the same, but just multiply by 2. And it is. So do it. Multiply by 2, but then don't forget to divide it out. And then you have the derivative of the bottom and the top, and voila. Now this guy, and I heard some people saying it over on this side, this guy should be obvious, it's always positive. You're raising the x to even powers on every single term, and you're adding. There's no way you're going to get a negative answer in there. So you can leave your absolute value off there. Any questions? Seeing is fun. All right. Now, I know some of you guys may be thinking, what do you do when the derivative of the bottom isn't in the top? And we'll look at some of that stuff, but some of it we won't be able to do yet because it just involves techniques that we don't know. But you're right. If you're already thinking about it, yes, of course there's going to be times when the derivative of the bottom is not in the top, and you can't just fix it with a little multiplication. Then you're going to have to do something else. So we'll see some of it today, but there's a lot of other techniques out there that we just don't have yet. And some of it we're not going to learn this year. Some of it we will, though. Let's look at this one. And here's one of them. Do, 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 do. So we got this guy. Now let's just work through this one together. Is the derivative of the bottom in the top? Yeah, definitely not. Now, here's something to notice about this problem. One thing to notice is this is not a proper fraction. What does that mean? Let me write it down though. The integrand, remember integrand, the thing inside the integral. The integrand is not proper. Sounds rather snooty. Does anybody know why this is not proper? What that means again? Yeah? Exactly. A proper fraction has a smaller degree on top. The degree of this fraction of the numerator is the same as the bottom. So if the degree of the top is the same or bigger, it's improper. So whenever, and this is actually true in general, if the integrand is not proper, I'm going to make sure I put the word not. If it's not proper, you need to divide to make it proper. Divide to get a proper fraction. And this is where now there's actually 3 different things I could think of to do this, to divide. First of all, can we do synthetic division on this? That would be really cool if we could, right? Can we? Yeah, we can't. Remember, you can only do synthetic division when your divisor is x minus k. That is x squared. So we cannot. Now, you guys are all coming from different teachers last year. I know I taught Polydoku for my students that had me, if you remember Polydoku. You may or may not have seen Polydoku. You may have just seen long division. Does that bring back memories? Long division? I hate long division also. I actually, to be honest, Polydoku is one of the few good things that the CPM books have brought to the world. And yes, I said that on the recording. I do not like CPM. So, I really actually hate CPM. But there are some gems in there. Polydoku is one of them. But we don't even, actually, if you think about this one, we don't even have to do long division or Polydoku. We got lucky on this one. It doesn't always happen. Does anybody see anything about this? Marcus? Exactly. And that is going to be useful. Why? How does that help? So we switch things. Big whoop. Do you notice anything, Charlie? That's right. I'll just write it out in steps so we see it. So remember, whenever you have multiple terms in your numerator, you can totally split it up into multiple fractions. Just keep the bottom the same. You're basically doing our adding fractions backwards. If you start at the very bottom that I have here, the fractions have the same denominator, so you can add the top and keep the bottom the same, and that takes you to the middle line, which just rearrange terms takes you to the top. And this first fraction is just equal to 1. Oops. So it's 1 plus x over x squared plus 1. Yay! And now, the derivative of the first term is easy. I'm sorry, the antiderivative. The integral of 1, that's x. But the second term now is a proper fraction. And do we have the derivative of the bottom and the top? Almost, that's right. We just need that 2, right? Now be careful about doing this. Do not just say, well, I'll multiply by 2 and divide by 2. That doesn't work on this one because the 1/2 would go to the 1. So do not write this. This would be bad. I'll come over and slap your hand if I see that. Sometimes I wish I could do things like that. Don't think that's allowed. I used to teach 7th grade out in Dallas, Texas. And this one mother came and dropped her son off on the first day of school. I still remember. He was cute little Dexter. Had this cute little pipsqueaky voice because he's 7th grade. He hadn't changed yet. And his mother just said, "This is my son Dexter. If he gets out of line, you've got my permission to smack him. You hear that, Dexter?" Dexter didn't know I couldn't hit him. Just the power. Dexter, remember what your mother said? Oh, sorry. Just made me happy. Sorry. I know. There's a sick part of me inside. Anyway, with this one, if you want to think about it in your head and then just do it, the antiderivative of 1 is x. Ooh, let me go back to pink. And then on the second one, we know we would want to put the 2 in there, so we'd want to divide by the half. So it's going to be 1/2 times the natural log of the bottom, which again, we know is always going to be positive because x squared is positive, and then you add 1, always positive. Or you could separate it into 2 separate integrals and do that. But anyway, there we go. There's that one. And again, you could put the square root. Write it as a square root if you wanted. Any questions about that one? Yes?
To prevent hand slappage, could we put the 1/2 on the outside and multiply both terms? So we have 1/2.
To avoid the hand slappage, you could actually do what I just erased from here. You could multiply by 2 and then just divide by 2 like this. And that would avoid the hand slappage. Yeah. I love this class. Any other questions on that one? See, they're progressively getting a little more interesting, right? All right, let's try this one. I don't know where I want to go. Go to a new one. And we'll do that. We'll walk through this one together. I'm trying to give you like all these different scenarios that you're going to see on your homework. So that's why there's so many examples. All right, the integral of 2x over x plus 1 squared dx. Hey, it's like Dexter, dx. I actually love the name Dexter. Anybody ever watch the show Dexter? Really? I didn't think it was that old. They're bringing it back. They're actually going to they're making a couple new seasons. Maybe just one, but I thought there was something like, anyway. Because fans were not happy about how Dexter ended, so they're going to make some new episodes. Anyway, if you're looking for something to binge watch, look up Dexter. It's about a serial killer. But it's kind of a quirky show. He's a serial killer that tries to blend in with society. He's got a code. He only kills people that deserve it. Whatever that means, right? There's another movie you guys should watch. What? Well, yeah, I guess you could call them serial killers. It's a bunch of them. So it's called The Last Supper. And it's about these grad students in Iowa, and they all live in this house together. And they're all very liberal grad students. But their big thing is they have people over for dinner once a week for conversation. And this all happens within like the first 5 minutes, so I'm not really giving anything away. But one of their cars breaks down, and it gets picked up by this truck driver and dropped off. And it turns out they have a spot open for dinner, so they go ahead, hey, thanks for being such a nice guy and driving me home. You want to stay for dinner? So he does. And it turns out that he's a very right-wing kind of guy, but almost kind of like, anyway, so they get into discussion, they get in this debate, and the guy ends up pulling a knife on them, and so kind of in self-defense, they stab him, and they kill him. But now they're freaking out. What do? We just killed this guy. Oh my God. And so they're worried that if they call, because they ended up stabbing him in the back to kill him, so it doesn't look like self-defense, so then they're worried. Oh my God. So they don't call the cops. They just bury him in the backyard. But now they're freaking out. They keep thinking about, oh my God, did we do the right thing? This guy's in here. And so they're talking over the next few days, and they come to the conclusion that, you know what? This guy was kind of a danger to society, right? Like, maybe we actually did a good thing. In fact, why don't we just make this a regular thing? We'll invite people over for dinner that don't agree with our views, and if we can't convince them by the end of dinner, we'll kill them and bury them in the backyard. Okay. And it's got a pretty good twist at the end. So that's it. It's The Last Supper. It's a black comedy, but it's a good one. What? I don't know, actually, because it's old. I watched it many, many years ago. God, it's probably like 10 or 15 years old now. It might have been made before you were born. But yeah, it's good. It's very good. And all this is being recorded for posterity. Okay. Anyway. Now let's take a look at this one. Do we have the derivative of the bottom and the top? Yeah. No. I mean, if you think of multiplying that, you could either do the derivative of the bottom with chain rule, or just think about x plus 1 squared is x squared plus 2x plus 1. Like, the derivative of the bottom is not in the top. We can't even multiply by something and fix that. Anybody got an idea? Zura?
Maybe add and subtract the
It's interesting. Let me just, so we have a visual here. The derivative of the bottom, which just to make life easy, I'm going to go ahead and multiply it out, but hopefully correctly. That would be the bottom. So the derivative would be 2x plus 1. So we have a 2x. We just don't have the plus 1, right? Did I screw up? Oh, plus 2. Yeah. I was just seeing if you were paying attention. Very good job, David. Yeah. But yeah, we could just add the 2 and subtract the 2, right? And that would balance it. Let's see if that works. Sometimes it does. Sometimes it doesn't. I don't know. So I'm going to rewrite this one then. Godzilla. We're going to add the 2 in there, and we're going to subtract the 2. It's still balanced then. And we get this. Which then means, think about this as 2 separate fractions. You have 2x plus 2 over x plus 1 squared. And then we have 2 over x plus 1 squared. So now the first one's good to go. We have the derivative of the bottom and the top. We know this guy's going to be natural log. So any questions so far? Because now the question is, did that help us? What about this guy? How do we integrate that? Marcus? Yeah. We can do U-Substitution here. If you have a composition of functions, then you can let U equal the inside function. Yeah. So this is going to be like 2 separate integrals that we're going to work out. we already know, if you don't see it, because it's been a while, you'll see it in a moment. We already know the first one. The first one is just the derivative of the bottom, or sorry, the natural log of the bottom. And again, that squared makes the bottom always positive, so we don't need absolute values. And then it's minus the integral, still working on this, the integral of this. But if we let u equal x plus 1, look at what happens. How does this whole U-substitution thing work again? We let u equal the inside function, but then what do we do with it? Right. Then you have to do you take the derivative of both sides? So the derivative of the left is du, the derivative of the right is just dx. Yeah. So now when we go ahead and substitute in, that 2 isn't part of anything, so it's just there. But then it's over u squared du. Did that really get us anywhere? How do we integrate that? 2 over u squared. The derivative of the bottom still isn't in the top. Trey? Sorry, say it again? Oh, yeah. Right, it is a negative exponent. It's power rule at this point. We can do power rule. This is really the same thing as 2u to the negative 2 du. And remember power rule. We got that too, so I'm just going to bring that out. But the power rule says add 1 to the exponent and divide by the exponent. And then we still have plus c now. Does this make sense? It's like all these rules now. This is where it's going to be complicated because we got all these different rules that are going to start floating around in our head that we're going to have to keep track of. That's why the homework's going to be so important. It's just practicing and getting them all like fluent. It's the fluency that you want. So one thing that I'm going to do, let's start cleaning up our work a little bit. I still have this term that I need to bring down every step of the way, but we're ready to go to our answer now. So now, let me know if this is too many steps at once, but I see this negative times a negative, so that's going to turn this into a plus sign. And then u to the negative 1 would be just over u, but we do have right above u is x plus 1. And there's your answer. Right there. Nice job. Nice teamwork. Good ideas from a lot of people here. So yeah, sometimes they get a little more complicated like this. A good rule of thumb, kind of make it, I'm trying to get the original one. Well, let me let you guys write that down and then I'll tell you the good rule of thumb. I don't want to make it too small while you're writing it down. Because there's two big things that we used here. We used integration using natural logs and integration using U-substitution. And by the way, the other thing too, and this is kind of what makes things a little, some people find it a little difficult in the beginning. This is actually not the only way to solve this problem. You can still get to the final answer a different way, but it's basically still using the same pieces. So looking back at that original problem, it's a fraction. The easy thing to check for, so I would recommend just checking for this. Is the derivative of the bottom and the top, or can you multiply by something to make it there? Because if so, do that. That's definitely the easiest thing. But if it's not, then what do? Well, if you notice what Suvrith noticed, then you could do that add and subtract thing to put the derivative of the bottom and the top. If you didn't notice that, though, the one thing that you should notice, the original problem had a composition of functions. If we on the original problem did U-substitution and let U equal x plus 1, this would actually all have still worked and got us down to here. If we had done U-substitution from the very beginning, we would have noticed then a natural log appearing in there. So this is not the only way to do it, but those are the two things to kind of look for. Derivative of the bottom and the top, and if it is, or if you can make it there with just a little tweak, go for it. The other thing, keep an eye out for compositions, because we still have U-substitution. Any questions about that? Let's go to one of our favorite things, trig. Oh man, I thought you guys would be jumping for joy when I mentioned the word trig. Yay! No? Okay. Now let's just, this does not count as like one of our 9 problems, by the way, but let's just remind ourselves the integral of sine x. What's that again? Nice. And then the integral of cosine. Is it positive or negative sign? Positive, yeah. And we stopped there. We didn't do any of the other trig functions. Until today! Dun, dun, dun! All right, let's do them. Yeah. The integral of tangent. We didn't know how to do this until today, but now we can. Based on what we've been talking about, does anybody have an idea what the trick is going to be? We're talking about natural logs and the derivative of the bottom and the top. That sounds like a fraction. Is there a way I can rewrite tangent to be a fraction? Charlie? Yes. Remember your quotient rule. Sine over cosine. Woohoo! Oh, wait, I don't want the plus c yet. What am I doing? And do we have the derivative of the bottom and the top? What's the derivative of cosine? It's close. It's really easy to get the negatives mixed up. The derivative of cosine is negative sine. So we just have the positive. So I'm just going to do multiply by a negative and divide by a negative. Let's make up for it. And then it's the derivative of the bottom, or natural log of the bottom. I keep saying derivative of the bottom. Then it's a natural log of the bottom. Any questions on that? Marcus? You definitely can. In fact, I'm going to write it both ways when we summarize. Remember that negative multiplying by a power rule of logs? We can make that cosine x to the negative 1, which means 1 over cosine, which means secant. So you'll also see it written like this. Either way, you have 2 possible answers for this. One is not necessarily better than the other. And then we could do something similar with tangent, or cotangent, I mean. I'm not going to bother doing that. We'll summarize all of our trig functions in a second. I just want to show you secant. How do we integrate secant? Because there's a trick on that one. You don't have to memorize this trick. This is a sneaky trick. But you do have to memorize at least what the antiderivative of secant is. So if I have the integral of secant, and I write it, hey, come back here. I just lost my train of thought. What? Oh, right. I was trying to remember what the trick was. I drew a blank. Here's a trick. It's not an obvious trick at all. You may be thinking, well, just write it 1 over cosine, do like what we did before, but then you don't have the derivative of the bottom and the top. You're not even close. So here's the trick. Here's what you do. We're going to multiply by a form of 1. Actually, let me change colors. We're going to multiply by secant x plus tan x over secant x plus tan x. And like I said, don't worry. I just want you to understand it. Don't worry about trying to come up with something like this on your own. But look what happens when we multiply by this. If I go ahead and multiply it out now, in the numerator we get secant squared x plus secant x tan x. And the bottom is the same. And now look at what we got. The derivative of the bottom is now in the top. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. The derivative of the bottom is in the top, so it's just the natural log of the bottom. So it's a natural log of secant plus tangent. It's kind of sneaky. Boom, boom. So, let's put a little summary of all of our trig functions together. Integrals of trig functions. Does that one, like I said, don't worry about like coming up with it on your own, but does that process at least make sense how it works now that you see it? All right, so integrals of trig functions. Remember, the integral of sine is negative cosine. And so the integral of cosine is positive sine. There's a nice pattern, just like with derivatives we had a pattern. There's a nice pattern with integrals too. Next up, I'm going to put tangent. The integral of tangent is negative natural log of the absolute value of cosine. So the integral of cotangent x dx is the positive natural log of sine. Look at the pattern that's happening. So with the first one, integral of sine, we know the answer to. So the integral of its cofunction is the opposite sign and then the cofunction. Same thing here. The integral of tangent is this. So the integral of its cofunction of cotangent is the opposite sign with the cofunction. The cofunction of cosine is sine. Now we did see on this one, on tangent, we also have this guy. But he's just like an extra added bonus. So then, the last one we just found the integral of secant is the natural log of the absolute value of secant x plus tan x plus c. Let me move this over so I have enough room. So the integral, of cosecant. Anybody want to try it just based on the pattern? Because it does follow the same pattern. Joshua?
Negative natural log of the absolute value of cosecant x plus cotangent x plus c.
That's it. Excellent. That's a sloppy plus C. Whoop. So if you can remember 3 of them, you got the other 3. And yeah, more stuff to memorize. Because remember, our good old friend, the AP exam, does not give you a formula sheet. You have to memorize these. All right, I just want to do one more problem. Just because I'm having fun. Are you guys having fun? Lie to me and say you are. Yeah, all right. Okay, thanks, guys. Let's do the integral of 1 over x natural log x dx. It's kind of a sneaky one, but it's also a classic one. Like this one just pops up in so many places. Remember this trick. It's not that sneaky, but anyway, definitely not nearly as sneaky as that secant tangent thing that we did above. Anybody notice it? Do we have the derivative of the bottom and the top? What, Marcus? Wait, what? Oh, yeah. I mean, right now, the way it's written, we don't. But all you gotta do is this. This is the same thing. Now is the derivative of the bottom and the top? Oh, yeah. So just be on the lookout for that. Because you'll see this guy pop up often enough. He's one to get familiar with. Get to know his name, ask him about his hobbies. Be friends. So what's the answer to this then? Is it just the natural log of x? Yep, nope. That's good. I'm seeing head shaking no. When the derivative of the bottom is in the top, then it's just the natural log of the bottom. So it may seem weird, but yeah, it really will be the natural log of the natural log of x. Boom, boom, boom. So there we go. Any questions? Whew! Happy Friday, right? All right, I'm going to end the recording. Bye-bye, people online.